Hello everyone. Today I am going to discuss with you the carbocations and their stability. This session will cover each and everything, what type of carbocations we do have, okay, and what is their stability criteria, how we can decide that this particular carbocation is more stable than the other. Many such type of questions are going to be asked in your paper like JEE means and the NEET entrance examination. So for any entrance examination you people are preparing, you please go through this complete session. My recommendation is please watch it till the end for having a complete go through knowledge on the carbocations and their stability. Me, your chemistry educator, I do teach you on Unacademy Plus, but here this is one of my session, which is the most curated session for you all, so that in one go you are done with the topic, and yes, you are assured to score +4 marks in your J means examination. Okay, so here we begin, guys. So first of all, I will be telling you what are carbocations. So whenever we see a positive charge over the carbon, it is being considered to be the carbocation. When it is having a carbon with a positive charge, it is expected to be bonded with 3 atoms and there is a positive charge. So how to understand this? We can easily understand this with the help of the hybridization. You all know that a carbon is having the electronic configuration that is helium. Then we have 2s2, 2p2. Okay. When the carbon is in its positive state, that is the C positive. When I am talking about not a carbon, I am talking about a C positive as an ion. Then the electronic configuration is said to be 2s2, 2p1. Okay. Then this carbon with a positive charge will undergo hybridization. So when you have to draw the orbital diagram, it will be like 2s2 with 2 number of electrons, and here we have a 2p with a 1 electron. This is 2p orbital with 1 electron. Okay, so these are my last shell, the valence shell electrons which will participate in the bonding. Okay, so here this carbocation, when it is in its ground state, this was the electronic distribution, but when this carbocation is in its excited state, then the electronic distribution would be something like this. That is, one of the electron from the s orbital will get excited to this 2p orbital, and here we will be getting this. Now ultimately what will happen? There is a concept of hybridization. These orbitals will undergo hybridization. Only these 3 orbitals will undergo hybridization, resulting into the formation of, there will be the intermixing of orbitals, and since the intermixing of orbitals will occur, they will redistribute their energy. Ultimately we will be having the 3 electrons of the same energies, and this is said to be sp2 hybrid orbitals. Okay, so the hybridization is sp2 hybridization. This is also the sp2 hybrid orbital, this is also the sp2, this is also the sp2 hybrid orbitals, and one of the pz orbital, if this was px, if this was py, this was pz, and one of the pz orbital will remain vacant. Okay, so I can say that this is the vacant pz orbital, vacant pz orbital. So when we have to draw the structure of such kind of carbocation, we must know that here we have 3 hybrid orbitals. So over a carbon with a positive charge, here we have a 3 sp2 hybrid orbital. So this is one hybrid orbital, this is the another hybrid orbital, and this is the another hybrid orbital. Hybrid orbitals are always having a major lobe and a minor lobe. Okay, so these are the hybrid orbitals, one with a major lobe and this is a minor lobe. So this major lobe is, why this is a major lobe? Because this has undergone the bond formation. Now they will be forming a bond with the hydrogen, hydrogen, hydrogen. Let's say they have been bonded with the hydrogen. So ultimately the 1s orbital of the hydrogen will form a bond with the hybrid orbitals. Okay, and over the carbon we will also be having a vacant pz orbital. So this vacant pz orbital will be a pure pz orbital, which is something like this, having a 100% p character. Okay, so this is my pz orbital. So this is the orbital diagram of this carbocation. So when you will see its bonding, you will find that we do have a carbon is bonded with one hydrogen, the another hydrogen you can form a bond with any other atom. the another hydrogen. Okay, this is the 3 CH bonds, and here we are having a vacant p orbital. So this is our vacant p orbital. Okay, so by this, what you will understand? By this thing, we understand that the carbocations are usually the 6 electron species. Why I'm saying 6 electron species? As we can simply see that here we have 1, 2, 3, 4, 5, 6. We do have only 6 electrons, so we can say that the carbocations are 6 electron species. They do have the 6 electrons. Okay, their octet is incomplete. Carbocations have, they have incomplete octet. And because they have incomplete octet, they are said to be electron deficient. We can say that they are electron deficient. Okay, they have a deficiency of how many electrons? They have a vacant p orbital. There is a presence of a vacant p orbital. They have a vacant p orbital. Okay, so because of the reason they are electron deficient, they have a vacant p orbital, they can accept the electron pair. So carbocations can accept the electron pair. Carbocations has a tendency to accept the electron pair. Why they want to accept the electron pair? To become stable, to complete their octet. So that's why the carbocations has a tendency to accept the electron pair to get stabilized. Okay, so that's the reason we are learning about the stability of the carbocation, to get stabilized. Okay, to complete their octet. Okay, so when we are talking about the geometry of a carbocation, the geometry of a carbocation should be like geometry of a carbocation should be a sp2 hybridized. They were sp2 hybridized. So for the sp2 hybridization, the geometry has to be trigonal planar. They must have a trigonal planar geometry. That is, a carbocation must have a trigonal planar geometry with a vacant p orbital. Okay, so the geometry has to be trigonal planar. So if my question is, out of all those geometries, this is also a carbocation, this is also a carbocation, this is trigonal planar, if you would see, this is a kind of pyramidal, this is also a carbocation, this is also a carbocation, which is something like bent shaped carbocation with a double bond. Okay, and this is also a carbocation, which is a kind of linear but sp hybridized. This is linear, so it must be sp hybridized. This is also something like bend shaped. This could also be the what type of carbocation? This is also sp hybridized. This is sp2. No, we cannot say that this is sp2, because for the sp2 the geometry has to be trigonal planar, which is not trigonal planar. So because so and so reasons, we can say that only this is the carbocation which is stable. This is the stable carbocation. Rest are not. Okay, so out of all the geometries, all the 4 geometries, only the carbocation with the trigonal planar geometry is the most stable carbocation. Is it clear? Now let's go through. Guys, when we see the carbocations, okay, now we have to know about their stability and how they can attain the stability. So to attain the stability, they have a 2 criteria. That is their charge has to be either undergo delocalization or dispersal. Okay, that is, a carbocation wants to disperse its positive charge. It wants to neutralize its positive charge. So before learning about the stability of a carbocations, let's have a look that what type of carbocations we could have. Guys, we could have a possibility of the formation of a carbocation, of such carbocation. This is a carbocation which is CH3CH2. Okay, so to understand the type of a carbocation, we always have to look for the alpha carbon. What? Look at the alpha carbon. If you are looking at any of the carbocation, please look at the alpha carbon. That is the carbon which is directly attached to the carbocation. That is the carbon which is directly attached to the carbocation. Okay, so I'm talking about this particular carbon. This is the nearest neighbor atom. Okay, so this is my alpha carbon. Look at the alpha position. So for this carbocation, when you will see that this is the alpha carbon, you will find that here we are having a three hydrogen atoms. Okay, we are having a three hydrogen atoms. This is simply an alkyl group. Okay, so this is said to be alkyl carbocation. Alkyl carbocation. Alkyl carbocation. Okay, we can simply say that this is an alkyl carbocation. Here, if you will see at the alpha position, this is my alpha. Alpha means the neighboring atom. Okay, so here the neighboring atom is not carbon but the oxygen. Okay, so we will look for this oxygen. So this is not a part of a carbon chain. We know that generally the organic compounds are basically the carbon containing compounds, but this is an heteroatom other than carbon. So this is said to be a group, has been substituted. So such kind of carbocations where at the alpha position we have a certain group, they are said to be the substituted carbocation. Substituted carbocation. Okay, now here if you will see, this carbocation is said to be, here we have a benzyl, this is a benzene ring, and this is a carbon. This carbon is usually said to be the benzylic carbocation. So this is known as a benzylic carbocation. Okay, now here if you will see, this is the phenyl ring. There is a difference. This is C6H5CH2, this is C6H5CH2, and this is C6H5. Okay, so this is phenyl and this is benzyl. Okay, so this part is known as benzyl. We call this as benzyl and we call this as phenyl. Okay, so this is a phenyl carbocation. Phenyl carbocation. First of all, I am telling you about the types of carbocation, then we will focus over their stability. Now here, this carbocation, this is a cyclopropyl ring and we have a CH2 with a positive charge. So this is being said to be the miscellaneous carbocation. You would be surprised to know, ma'am, why you are saying that this is a miscellaneous carbocation? Yes, because this is a miscellaneous case and this is a cyclopropyl methyl carbocation. Okay, so this is a cyclopropyl methyl carbocation, and this is considered to be the miscellaneous carbocation, and this is exceptionally very stable. I will be telling you all about it. Exceptionally very stable. Okay, so some of the times many of you have heard about a kind of a dancing resonance. So dancing resonance is nothing as such. Okay, but still, what is the criteria, how this carbocation is exceptionally stable, I will be discussing all about it. Okay, so right now you please consider this as an example in the miscellaneous carbocation. Okay, which is an exceptionally stable carbocation, cyclopropyl methyl carbocation. Now here, this, whenever we have a pi bond and along with the pi bond here at the alpha position, if we have a positive charge, such positions are known as allylic positions. Okay, this is then known as allylic carbocation. Okay, now here if you would see this, so here what is this, this is, if you would see, you will find that this is an aromatic ring. Figure it out, guys. This is a closed cyclic ring having a planar geometry. There is a delocalization of pi electrons. This is also obeying the Huckel rule. So considering all the factors, you will find that this is an aromatic carbocation. So we may call this as the aromatic carbocation. And if you will see this particular structure, you will find that here we do have a closed cyclic ring, planar, delocalization is there, but here the number of pi electrons are 4. So this is said to be, this is obeying the 4 and pi electron rule, which means this is an anti-aromatic carbocation. Anti-aromatic carbocation. Got it? So this is the criteria in which we have distributed all the types of carbocations: alkyl, substituted, benzylic. So what type of carbocations basically they are? Okay, so this is it. Okay, if you do have any other example like this, let me give you an example where you have a benzene and this is your carbocation, and here the OCH3 group is being substituted. So such carbocations where we have any ortho or para substituent are also said to be the substituted carbocation. Okay, whenever we have any such kind of groups which is an hetero group, whether OCH3 or whether NH2 is there, or whether any kind of chlorine, bromine, iodine, anything like this, if there is present other than carbon, then they are said to be the substituted carbocation. Got it? So this is also an example of substituted. So these are the types of carbocations. Now the question is, okay, we understood what we can call them. Now how to understand that what will be the stabilizing factor? Carbocations usually get stabilized by what? Carbocations are usually get stabilized by three things. Okay, basically, too stable, too stable, you need to neutralize them. Carbocations, you already know, they are the 6 electron species. Okay, they are the 6 electron species, so they basically wants 2 electrons. So the question is, who can give those 2 electrons? Okay, so they basically wants to stabilize. That's why they are looking for any of the species, those who can give the electron pair. Okay, so these carbocations can be stabilized by the lone pair, by the lone pair. If at any of the alpha position, if this is my carbocation and this is the alpha position, sorry, let me rub this just a minute. Let's say if this is my carbocation, this is my carbocation, and this is the alpha carbon. For this carbocation, this is the alpha position. If here at this alpha position we have to look, alpha position, this alpha position we have to look, what we do have. Okay, alpha position is basically the nearest neighboring atom. Okay, so at this nearest neighboring atom we have to see what we do have. If we do have a lone pair, if we do have a lone pair, this will stabilize it. So carbocations usually get stabilized by a lone pair. Lone pair. How does a lone pair stabilize it? Lone pair basically show the synergetic effect. This lone pair basically show the synergetic effect. Synergetic effect, or you can say that, this shows the back bonding. This shows the back bonding, synergetic effect or the back bonding. Because of that synergetic effect or the back bonding, it stabilizes the carbocation. The another factor, the major factor is basically the pi bond. So here at the alpha position, here at this alpha position, if we do have a pi bond, okay, that is the pi bond. So pi bond are basically the loosely held electrons, and they are very nucleophilic in nature. Okay, they are good nucleophiles. Okay, so this pi bond is also a weak bond which can easily be broken and can give its electron pair to any of the carbon with a positive charge, and so therefore lead to the stability. So this pi bond can stabilize, and when a pi bond gives the electron to the positive charge, this is said to be the resonance, means by the resonating effect. How this can be done? This can be done by the resonating effect. There will be an stability. The third factor is, if you don't have any lone pair, you don't have any pi bond, you might have a sigma bond. You might have a sigma bond. Okay, you might have a sigma bond. So what happens in the case of a sigma bond? So when you have a sigma bond, so basically the sigma bond, that is the sigma bonded hydrogen, if you do have sigma bonded hydrogen, if you do have, this will stabilize the carbocation by the effect that will be known as the hyperconjugating effect. Hyperconjugating effect. I will tell you everything, so don't worry about it. Okay, as I said, please watch the lecture till the end. Okay, everything will get covered. Hyperconjugating effect. Okay, so basically more the number of alpha hydrogens, more is going to be the stability. Got it? This is the point which I want to make. So basically any of the species that can give its lone pair or a pi bond or these alpha hydrogens will try to stabilize. Let us figure out here. If you would see the examples like this, The examples like this lone pair, pi bond, and this. Okay, I have picked three examples. Okay, so just focus over those three examples. If you will see the example number one, here we do have the alkyl carbocation. So when you will see this alkyl carbocation, you will find that here we have a CH3 CH2 positive. At this alpha position, what we do have? Do we have any lone pair? No. Do we have a pi bond? No. Do we have the alpha hydrogen? Yes. So at this alpha position, we have these alpha hydrogens. So because of these alpha hydrogens, okay, there will be the sigma bond resonance, that is the hyperconjugation, and ultimately this will leads to the stability. So here, for which factor is applying? That is the sigma bonded hydrogen. Sigma bonded hydrogen, that is by the hyperconjugation. By the hyperconjugation, this is getting stabilized. Okay, now how many alpha hydrogens? There are three alpha hydrogens to stabilize this. Now you will see the example number 2. Here in the case of the example number 2 that I have picked is basically the CH2 positive, and over the oxygen I am having a lone pair. You know oxygen is having a lone pair of electron. Absolutely. If you will see the valence shell electron over the oxygen, you will find that this is 6 electrons. 2 are in bonding and 2 are lone pairs. So ultimately this is the alpha position, and this alpha position oxygen lone pair. So oxygen will show the back bonding. This will show the synergetic effect. Okay, this is the neighboring atom. This will show the synergetic effect and leads to the stability. Ultimately, what we will be getting, we can say that because of the lone pair, this is getting stabilized. So lone pair, so basically which effect is this? That is the synergetic or the back bonding. Because of the synergetic effect, this is getting stabilized. The third example is this example which I took. So here if you will see, this is a carbocation. So how this carbocation will get the electron? This carbocation will get the electron from this pi bond. So here we can say that because of this pi bond, this is getting the electron. That is the reason is pi bond. And which effect is this? This is the resonating effect. So because of this resonating effect, we are getting our carbocation stabilized. Okay, so basically guys, for a carbocation, carbocation is the deficient. If you are talking about a carbocation, this is deficient. Okay, so see, one has to take and the other has to give. Are you getting my point? The carbocation is saying that I am deficient, is begging for the electron, and the other groups, whether the sigma bonded hydrogen or the lone pair or the pi bond, they are behaving like a donor. Okay, they are behaving like a donor. So whenever there will be a relationship of like a begging and a donating, so you always know that a beggar keeps his or her hand downwards and always a donor has its hands upwards, right? So what I want to make you understand is the carbocation, which is asking for the electron, is basically lower in its energy. The energy of that particular carbocation has to be low. Okay, so carbocation is in its low-most state. That is, this is the lowest unoccupied molecular orbital. We can say that this is the lowest unoccupied molecular orbital, and any of the species which is at the alpha position who is giving its electron pair, whether with a lone pair, whether with a pi bond, or whether with a sigma bond, whatever the way, if they are giving their electron pair, so they must be in their higher energy state. That is, they must be in their high energy state. That is homo. So what do you mean by homo? Homo means occupied highest occupied molecular orbital. Highest occupied molecular orbital means their energy, means any of this thing which is giving its electron pair has to be its high in energy. Its energy has to be higher. And the species which is taking the electron, its energy has to be lower. ठीक है, its energy has to be lower. So this must be here and this must be here. Okay, so if I'm talking about their energy states, this must be high in energy. Any of the species who is giving its electron pair must be higher in energy, and any of the species which is asking for the electron has to be lower in the energy. Okay, so this is homo, the energy is the highest, and here the energy is the lowest. Okay, then only the stability will occur. Okay, so this means that, so homo, if I'm saying, means they have to be a better nucleophile, they have to be a better giving in nature. Okay, so this means that any of the species which is a better nucleophile will better stabilize the carbocation. So in another words, we can say that they have to be a better nucleophile. Okay, they have to be a better nucleophile so that they can stabilize the carbocation. So if I ask you, out of the lone pair or a pi bond or a sigma bonded hydrogen atom, if I ask you which is a good nucleophile, which is a good donor who has higher energy state, then your order comes out to be, that is a lone pair, that is a lone pair is always a good donor, then the pi bonded electron, then the sigma bonded electron. Okay, so if I will compare, because lone pair is only under the influence of only one atom, the pi bond is under the influence of two atoms, and if you will compare the pi bond and the sigma bond, this is also under the influence of two atoms, but here we have a effective overlap, a strong overlap, but here we have a sidewise overlap. Okay, which can be easily broken and can be easily given. Okay, so that's why we can say that the pi bond is a good nucleophile than the sigma bonded electron. So here, out of these three examples, that is example number 1, 2 and 3, if I ask you the stability order, if I ask you the stability order, then what will be your answer? If I ask you the stability order, your answer has to be, that is the lone pair one is going to be more stable, that is the option number 2 is going to be more stable. Then the pi bonded species, that is the structure number 3rd, is going to be more stable than the structure number 1. Are you getting it? Second is more stable, because in the second we do have a lone pair, in the third we have a pi bond, and then in the last we have a sigma bonded electron. Okay, so 2, 3, 1 will be the stability order for these three questions. Okay, so this is how we can understand. Now guys, let me give you the stability order for the carbocations. Okay, so it was just to tell you that which is going to be a good nucleophile. Yeah, you do follow this. Else, to cover every question, every example, we need to understand that the stability of carbocations would be in such a order. That is, any of the carbocation which is aromatic is going to be more stable. Now, if I ask you the aromatic, what does this mean? Let us figure it out. Guys, this simply means that any of the compound, if I say I do have a compound like this is aromatic. Okay, this is aromatic. Why this is aromatic? Because this is cyclic, this is a closed cyclic ring. Okay, and this is planar, there is a complete delocalization and obeying the Huckel rule. So this is an aromatic compound, and because this is an aromatic compound, this is said to be highly stable in nature. Okay, now the miscellaneous case I considered with you the cyclopropyl methyl carbocation. Okay, the cyclopropyl methyl carbocation, this is the carbocation I considered. That after this the miscellaneous category will come, and in the miscellaneous category we have only one single example, that is the cyclopropyl methyl carbocation, this. So why is this more stable? The reason is, you know, let me explain it to you here. If you will see the cyclopropyl carbocation, absolutely. Okay, so basically this is its alpha position. Over the alpha position we want to look whether this will be able to give its electron pair or not. Okay, so now if you will see the cyclopropyl ring, usually a carbon whenever a carbon we do have, these are all the carbons which are sp3 hybridized. Okay, these are all the carbons which are sp2 sp3 hybridized. This is also the hydrogen, 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 hydrogen. Okay, so these are the carbons which are usually the sp3 hybridized. So a carbon when it is sp3 hybridized usually have a bond angle of 109 degree 28 inches, right? But here we can see that this is a triangle. Okay, this is a cyclopropyl. So because of the cyclopropyl, here the angle is going to be the 60 degree. So here the bond angle is not 109 degree. Here the bond angle is being decreased to bond angle has been decreased to 60 degree. So means there is a decrease in bond angle. Okay, so guys, for the 109 degree 28 inches, we know that the hybridization is sp3. Okay, for the 60 degree and for the bond angle 120 degree, we know the hybridization is said to be sp2. For the bond angle 180 degree, we know that the hybridization is said to be sp, right? We know that the bond angle and the percentage of S character are directly related to each other. That is, bond angle is directly proportional to the percentage of S character. You all know that, right? So this means that when the bond angle is greater, the percentage of S character is higher. So here if I evaluate the percentage of S character, it is 50%. Here it has been decreased to 33.33%. Here if you will see in the case of the sp3, it will decrease to 25%, means I have only 25%. So if my bond angle is decreased from 180 to 120, 120 to 109, 109 to 60 degree, because here the bond angle is 60 degree. So when the bond angle is decreased to 60 degree, I can expect that the percentage of S character decreases more, right? I can expect that here the percentage of S character is going to be decreased, is going to be only 5% or something. Let me say that it is nearby equals to the 5% only, because the bond angle is decreasing more and more. Okay, 5 to 10% I can say that. So ultimately, if the S character is decreasing, so what does this mean? Now let us look for the energy diagram. So when you will see the energy diagram, you will find that the S character, here we do have a 100% S character. Then we could have a SP, then we could have SP2, then we could have SP3, then we could have P, right? SP, the percentage of S character is 50%. 50% as character, here 100% as character, here 33.33% as character, here 25% as character. And now I'm saying that I'm not saying that there will be no hybridization. There could be hybridization. Now only I can say that the S character is going to be approximately is equals to 5% as character. That is, the S character is decreasing. So when the S character is decreasing, so when this S character is decreasing, I was expecting this to be here, but here the energy is increasing. So because of this reason, this is a cyclopropyl ring having a bond angle of 60 degree. As the bond angle decreases, the S character decreases, and since the S character decreases, the percentage of S character decreases, the percentage relatively, the percentage of P character increases. Okay, so P character increases means energy increases. Energy, which energy is increases? Basically the HOMO, that is the highest occupied molecular orbital. The energy of the nucleophile increases. So guys, here this bond, the bond we are talking about, this particular bond, the nucleophilicity of this bond increases. I can say that the energy, that is the HOMO, highest occupied molecular orbital, energy increases. Energy increases because of more percentage of P character. As the P character increases, the energy increases. As the energy increases, this becomes a better nucleophile. this becomes a better nucleophile, okay, as compared to that of the other carbocations. Since this becomes a better nucleophile, now let me tell you. So because of this reason, this ring has to be a sp3 hybridized as that is 109, but here in this ring there is an angle strain. So because of this angle, there is an angle strain, we can say that, okay. Because of this reason we can say that there is an angle strain. Because of this angle strain, we were expecting that they will be forming a bond like this, and so therefore there is a formation of the sigma bond, but actually not. This bond is not like this. There is no headed overlap. There is an angle strain. This overlap is basically slightly like this. Because of this angle strain, this overlap is something like this. So rather than being a pure S, they have more of P character. Okay, rather than it is being considered to have a complete S character, that is, it's a sigma bond, it is basically having a P character. Okay, this is having a P character. And here in the case of the carbocation, that is CH2 positive, we do have a vacant orbital there, we do have a vacant P orbital. Okay, so basically because of the reason this bond is not like this is something like this bent. So this and this becomes more close to each other. Okay, if you will see this and this, you will be able to see the difference. You will be able to see the difference. So here and here, this gap is large, this gap is large, but here this gaps become smaller. Okay, and because of the increase in P character, this becomes a better nucleophile. This becomes a better nucleophile, and so therefore, it the tendency to give the electron pair increases. Okay, the tendency to give the electron pair increases. So whatever the overlap you see, they are going to have this kind of overlap. Okay, because of this angle strain, this could not be over the line, this could not be a headed overlap. Okay, so this becomes a better nucleophile, and this has a tendency to give the electron pair more easily. So what I said for a carbocation to stabilize, carbocation is basically asking for electron, it is behaving like a beggar. Okay, so if any of this species becomes a good nucleophile and can give the electron pair very easily, will stabilize it faster. Okay, so here that's why the cyclopropyl methyl cation gets stabilized by this sigma bond. By the sigma bond. So sometimes people say that this is a dancing resonance, this is a sigma bond resonance. Here this is a sigma bonded electron which is resonating. But in actual terms there is no such words. There is no such word like dancing resonance. Okay. So basically this is a hypothetical structure. Okay, we can evaluate that, we can think that yeah, hypothetically this is what could happen because of the angle strain. The energy increases, as the energy increases, this would easily be able to give the electron pair to the carbocation. Okay, and because of such and such reasons, we have found that for this kind of carbocation, okay, carbocation, this species can give its electron pair. Okay, so when this will try to give its electron pair, what can happen? This can give the electron pair to this. So we can draw the resonating structure, something like CH2. This will become this, and because the bond is getting broken from here, we will be getting a positive charge from this side. Okay, or you can say that here this will also show the resonating structure, something like this. We can break a bond from here, we can break a bond from here, right? So this could also becomes like CH2 C, this bond can go there, and ultimately here we will be getting a positive charge. So these could be the resonating structures. So basically out of all the three structures, no one is going to be an ideal structure, no one is going to be a true structure. Basically we can say that the electrons are keep on resonating. Okay, the electrons are keep on resonating between this or this structures. Okay, and so therefore sometimes this is being called as that this sigma bond is showing the resonance, and this is being considered as sigma bond resonance or a dancing resonance. Okay, but if you ask me, I would say rather than saying it a dancing resonance or something else, it's better to understand the nucleophilicity. Okay, the energy diagram. Okay, so because as the angle decreases, the S character decreases, the P character increases, and since the P character increases, the energy increases. This is your energy level diagram. Here we are talking about the energies, right? So since the energy increases, this becomes a better nucleophile, and since it's a better nucleophile, it is giving its electron pair very easily. It is getting more stabilized. Okay, so this is the explanation for this cyclopropyl carbocation. Okay, now here we can take another example, that is the substituted carbocation. Now what do you mean by the substituted carbocation? I took some of the examples like CH3O CH2 positive. Okay, so yes, absolutely, this is a substituted group. Okay, and even if I take any such example like this, and here I put OCH3. This is also a substituted group. Here the substituted carbocation is getting more stabilized because of the lone pair effect, that is the synergetic effect. Because of the synergetic effect, this will get more stabilized. And here how it will get more stabilized? Here because of the oxygen's lone pair, this will show the plus M effect, that is the mesomeric effect. So ultimately because of this mesomeric effect, the electron will delocalize and will stabilize this carbocation. So these are considered to be the substituted carbocations. Okay, so this effect is known as the synergetic effect, that is the back bonding, and this is your plus M, that is the mesomeric effect. Now here what is the difference with a resonance? Okay, so what do you mean by a resonance? Guys, the resonance carbocations could be of many types. That is, this is a carbocation which can show a resonance. This can also a carbocation which can show a resonance. Okay, now these are the two carbocations which can show a resonance. Now let me talk about this. Guys, if you will see this pi bond and this, here I told you whenever at the alpha position you do have a pi bond. So this pi bond is a good nucleophile. This can easily give its electron pair. So ultimately this pi bond will be broken and this will give the electron pair to this carbocation. Ultimately because of the resonance, this is a XYZ system. This will get stabilized. Here if you will see again, this is a carbocation. Here we do have a pi bond. If you will see the alpha position, over the alpha position we do have a pi bond. Okay, and because of this pi bond can easily be broken and can give the electron pair to this carbon and can stabilize. So this is also known as the resonance carbocation. Now many times students gets confused between the structure this and the structure this. If you will compare, you will find that this is more stable than this. You would say, ma'am, this is aromatic. Oh, ma'am, this is also aromatic. Right? Why you would say? This is aromatic. This is also aromatic. Let me make you understand. What is the difference between the two? The difference between the two. Basically, when we are saying that this is a species that we do have, okay, and we are saying that this is a species that we do have, there is a big difference between the two. Okay, this is a benzene containing ring. This is a benzenoid compound, but this is not a benzenoid compound. But if you will see both of them together, this is quasi aromatic. This is quasi aromatic. Yeah, we can say that this is aromatic. Okay, but here is this carbocation is aromatic? No. See, what is this? What you can understand? This is a benzenoid compound. This is a benzenoid ring. This is a benzenoid ring. Or you can say that this is a benzylic carbocation. This is a benzylic carbocation and this is an aromatic carbocation. This is an aromatic carbocation. There is a difference between the two. We can say that this is an aromatic carbocation. Why? Because this positive charge, which is a cationic positive charge, is a part of this aromatic ring. Aromatic compounds are those compounds which are having a closed cyclic ring. Okay, closed cyclic ring, planar. There has to be a delocalization of pi electrons. Okay, and they must follow the Huckel rule, that is 4n plus 2 pi electron rule. So if you will see here, we do have 6 pi electrons. Okay, this is a closed cyclic ring, planar delocalization of pi electron, and this carbocation is a part of that delocalization. Okay, and the carbocation is a part of that ring. That's why we can say that this is quasi aromatic. This concept is known as quasi aromatic. I have already created one of the session on this, you can go through that. Rest I am repeating it here. And this is a benzylic carbocation. We can't say that this is an aromatic carbocation. Can you say that this is an aromatic carbocation? No, 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 no. Why no? Because this positive charge is not a part of that aromaticity. This ring is aromatic. This ring is aromatic. There could be a delocalization. The ring is aromatic. The ring is cyclic closed ring. But carbocation is not aromatic now. Okay, so this is the difference. Okay, so this is a species, so this will get stabilized. So my question is not about the stability of a ring. I was questioning you for the stability of a carbocation. So who is stabilizing my carbocation? Is the ring? Is the delocalization in the ring? No, delocalization in the ring is not stabilizing my carbocation. My carbocation is getting stabilized by the resonance, by the resonance with these pi bonded electrons. Got the point? So here this is getting stabilized because of the aromaticity, and here it is getting stabilized because of resonance. So the factors which are stabilizing both of them are different. Okay, so that's how we can say that this is a resonance stabilized carbocation, this is an aromatic carbocation. Okay, and if we will compare between these two, now this is also resonance and this is also resonance. If you will compare in between these two, now which is going to be more stable? This is a pi bond and this is a benzene. Then the reason is both are stabilizing by resonance, but this is a benzenoid compound. Since this is a benzenoid compound and this is a non-benzenoid compound, so we can say that the benzenoid compound is more stable. This is more stable and this is less stable. Got it? Now we could have some of the examples of the hyperconjugation. Now what do you understand by the hyperconjugation? If you will see, then we do have the compounds with carbon with hydrogen, and this is a CH3, this is a carbocation, that is CH2 positive. So if you will see over this, it's alpha position. So here at this alpha position there is a lone pair, no, pi bond, no, nothing is there, no ring is there. So what is there? There is a sigma bonded hydrogen atom. So sigma bonded hydrogen. So now how many alpha hydrogens? Look at the alpha position only. No other position will work. Look at the alpha position only. So if you will see, here are only 2 alpha hydrogens. So these 2 alpha hydrogens will be responsible to stabilize this carbocation. Okay, that is these 2 alpha hydrogens. That is the reason is hyperconjugation. Okay. Now, what do you understand by the percentage of S character? Percentage of S character. As I told you, we could have the we could have the the carbocation, which is something like this. Okay, here this is sp2 hybridized. We could have a carbocation which could be like this. You know, this is sp hybridized. So out of these two carbocations, which is going to be more stable? The one with the less percentage of S character. Okay, so what I told you, more with the percentage of P character, more will be the energy and more will be the stability. Okay, so they have to be higher in their energy. So the as the percentage of S character increases, percentage of S character increases, stability decreases. Okay, so here this is better stabilized. Here the percentage of S character is how much? 33.33%, and here the percentage of S character is 50%. Okay, so out of these two, this is more stable than this is not. Okay, percentage of S character determines the stability. Then comes your such kind of compounds. And then the last is anti-aromatic. I have already shown you one of the example of anti-aromatic, like this. So if we have any kind of ring which is anti-aromatic, so this carbocation is basically anti-aromatic because this is a part of the conjugation. So such kind of carbocations are least stable. Least stable. So got it. So please do understand aromatic. Then comes your miscellaneous. Miscellaneous carbocations are exceptionally stable. Okay, mark it. They are exceptionally stable. Substituted whenever any kind of group is substituted, whether it is methoxy group, nitro group, NO2 aa gaya, NH2, or any kind of halogen, or any kind of cyanide, or hydroxyl group, any kind of group is, if it is there, okay, they will be considered to be the substituted. Then comes your resonance, which are getting stabilized by the lone, by the pi bond. Hyperconjugation, that is by the alpha hydrogen, the percentage of s character, and the anti-aromaticity. So if you will try to, please learn this whole part. Please learn this whole part. Which part? Here, this part, this much. Okay, that is the aromatic, miscellaneous, substituted, resonance, hyperconjugation, percentage of S character, anti-aromatic. You will be able to solve each and every question. I have some practice questions for you all, so we will have a look on that. Okay, so here it's not yet over. Guys, if you will relate this particular point, the lone pair pi bond and sigma bonded resonance, you can relate with these points as well. They are 1, 2, 3, 4, 5, 6, 7. There are 7 things that you have to focus. So lone pair, in the substituted part, here the lone pair was working. Here there was a pi bond, and in the hyperconjugation the sigma bonded electron was there. Okay, so ultimately what comes? Aromatic, miscellaneous. Please learn with me. The aromatics are most stable. Aromatics are most stable. Anti-aromatics are least stable. Okay. After aromatic, there comes a special case, that is a miscellaneous carbocation. The example is cyclopropyl methyl carbocation, okay, which is exceptionally stable because of that ring which has a strain, because of the reason it breaks itself and give the electron pair to the carbocation. Okay, and here the percentage of p character increases. So p character basically results into the formation of a partial pi bond. Okay, so we can say that here we have a partial double bond character. So because of that reason, this is getting stabilized. The ring is getting broken and giving the electron to the carbocation. Then comes your, after that we know that our three agendas, the three things which are extremely helpful to us, that is the lone pair. First, lone pair is a better nucleophile. Then comes the bonded pair, the pi bond. Then comes the sigma bonded electron. Then comes your percentage of S character. Last is anti-aromatic. Okay, so this is how the 7 can done. Got it? So here, let us move. I discussed with you the miscellaneous carbocation, the quasi-aromatic and the aromatic, the difference between the quasi-aromatic and the aromatic compounds. And the aromatic, I would better say aromatic compounds. Okay. Now here we do have few examples. Example 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I believe you people are ready to answer me all such questions. So let us do all of them. So in the question number 1, if you will see, which is more stable? So my way of doing is, okay, so please learn what approach I'm putting, okay, and learn from that particular approach. Okay, this is a carbocation. Okay, this is my alpha position. What this alpha position will give me? This is other than carbon. This is some kind of atom. So I would first say that this is a substituted carbocation. And here what the substituted carbocation will do? Here we do have a lone pair. So I can simply see that there is a synergetic effect. Okay, because of the synergetic effect, the back bonding, there will be the stability. And here in the case second, we can see that this is a carbocation and this is the alpha position. At the alpha position, I do have a pi bond. So when I do have a pi bond, what can happen? Is this a aromatic carbocation? No, this carbocation is not a part of that aromatic ring. So not aromatic carbocation, this is resonance stabilized carbocation. So here I can have the resonance, I can have the resonating effect. Okay, so what was the order? The order was aromatics are more stable, then comes your miscellaneous. Okay, after miscellaneous there were 7, no? So after miscellaneous, what was there? There was a lone pair, that is the substituted carbocations. After substituted the pi bonded carbocations, that is the resonance. And after resonance there was the hyperconjugation, right? Substituted lone pair, pi bond and alpha hydrogens. After that there was the percentage of s character, and then in the last there was anti-aromatic. Okay, so if this is the way you will learn, you will be able to figure it out and you will be able to answer every question. So substituted and a resonance. So who will better stabilize, a lone pair or a pi bond? We know that lone pair stabilizes better than a pi bond. Okay, so the answer is this. So this is the correct answer. Done. Now do the question number 2. In the question number 2, we do have a carbocations, and here in these carbocations, this is the alpha position, alpha position, alpha position. There are 3 alphas. Okay, there were only one alpha, but this alpha is also the same. And here we are having, this is a carbocation, this is the alpha position, and this is the alpha position. Guys, this hydrogen is basically over this carbocation itself, so this will not be considered as the alpha. Okay, no, because this has been bonded to this carbon directly, so this is not alpha position. Okay, because we can only give the position to the atom, not the hydrogen. Hydrogen is there to complete its valency, okay, to complete its octet. Okay, now here for this carbocation, no hydrogens, only this is the alpha. Okay, so if you will see, there is no pi bond, there is no lone pair, there is no aromatic miscellaneous, nothing is there. We can simply see that there we have the alpha hydrogens. Alpha hydrogens. So if you will see how many alpha hydrogens we have, sigma bonded hydrogens, 3, 3 and 3. Here we have 9 alpha hydrogens. Here we do have 3 and 3, that is we have 6 alpha hydrogens, and here we have only 3 alpha hydrogens. Okay, so all the carbocations are getting stabilized by hyperconjugation. So hyperconjugation is the thing. All are getting stabilized by hyperconjugation. And guys, hyperconjugation, more is the number of hyperconjugating structures, more number of alpha hydrogens, and more number of alpha hydrogens, more will be the hyperconjugating structures, hyperconjugating structures, and so therefore more will be the stability. More will be the stability. So ultimately we can conclude that this is going to be more stable than this and then this. Okay, so this is the way how we will answer the question. Example number 3, CH2 double bond CH single bond CH2. If you do have any doubt, please mention it in the comment section. This is the first that you could do. Okay, so here we do have the example number 3, which is CH2 double bond CH single bond CH2. So if you will see the alpha position, what you can figure it out? Yes, we have a pi bond. So pi bond, how this pi bond will stabilize this? By the resonance. So which factor is working here? Resonance is working here. Here if you will see, this is a carbocation and this is the alpha position. Who will stabilize this? Again, our reason is pi bond. That is a pi bond. Okay, so pi bond means the effect would be the resonance. If in both the cases I do have a resonance effect. Now how to identify which is more stable? Resonance is resonance. Then guys, you need to understand that this is a benzenoid ring. Okay, and this is a benzylic carbocation. This is a benzylic carbocation having a benzene ring, and this is a allylic carbocation. Allylic carbocations, they both stabilize by resonance, but there is a difference. This is a benzenoid ring, and because of the benzenoid ring, this is going to be more stable. Always remember, benzylic carbocations are more stable than the allylic carbocations. Okay, when you will draw the structure, you can get many number of resonating structures for this benzylic carbocation, and here you can get only 2 resonating structures. Okay, that's the reason. Now here in the case of example number 4, what you can see, this is a carbocation, this is a carbocation, the alpha position, both the alpha positions are same. Nothing we can evaluate, all are same, the benzene is same. Ultimately we found that here we have OCH3 and here we have NO2 group. So ultimately we can say that these are the substituted carbocations. Substituted. This is a OCH3 group substituted, and this is also a substituted carbocation. There we have NO2 group. So what type of substitution we do have? So if you will see here, you know, over the oxygen we have a lone pair. So this lone pair and a pi bond. Who is a better nucleophile? Who is better donor? Pi bond or a lone pair? Lone pair is a good donor. So this lone pair will give the electron pair to this part, then to this, then to this, and this will ultimately show the plus M effect. Ultimately, the electrons are getting delocalized to stabilize the carbocation. Okay, and here if you would see, you will find that here in the case of NO2, this is a pi bond and this is also a pi bond. So now which pi bond will be broken first? This is a polar pi bond. Polar pi bond. There is a polarity. Over the nitrogen, there is no lone pair. The lone pair is undergoing the formation of this coordinate bond. So there is no lone pair. So ultimately, this is a pi bond, this is a pi bond. If you will see compare both the pi bonds, you will find that this pi bond is a polar pi bond. Ultimately, the oxygen will pull the electron. This will go like this. This will go like this. Oh, ultimately, we are pulling up the electrons from the carbocation. So this is showing the minus M effect. So who is stabilizing? Bache, the carbon is saying I'm deficient, I'm a 6 electron species, I need electron. So the species which is giving the electron to this vacant orbital is basically more stable. So here this is more stable because this is showing a plus M effect. Okay. Okay, so when you have a carbocation and a carbocation is saying, oh bhai, I am very deficient, you please give me the electron. So any of the thing whosoever will give the electron is going to be a better stability, will provide a better stability. So we need a better nucleophile. We need a better nucleophile to do the stability. Okay, so we can say that if it is deficient, this has to be richer. That's the neutrality is the key. Okay, if this wants electron, you please give the electron. So it will attain the stability. Okay, now here let's go with the example number 5. If you will figure out this example, that is example number 5, what you can see in between the two. They are a closed cyclic ring, both are closed cyclic ring. This is also cyclic, and the carbocations are a part of that ring. But here if you will see, there is a delocalization. There is a delocalization. There also we do have a delocalization. I know you got the answer. Okay, there is a planarity. There is also a planarity, but here the number of pi electrons are 6 pi electron, that is 4n plus 2 rule is being obeyed. But here the number of pi electrons are only 4, that is 4n pi electron rule is obeyed. So what does this mean? This means that this is simply an aromatic carbocation and this is an anti-aromatic carbocation. Anti-aromatic. So out of these two, which is more stable? You know the example, that is the one which is aromatic is more stable than the anti-aromatic. This is the answer. Example number 6. If you would see the two examples, what you can compare? Here guys, you can see that this and this. This is the alpha position, alpha position, alpha position. Alpha, alpha, alpha. Over the alpha we have a benzene ring. We do have a pi bond. We do have a pi bond. We do have a pi bond. So who will stabilize this? Pi bond. Pi bond, this means, pi bond means resonance. Resonance will stabilize this. And here if you will see the alpha position, we do have the sigma bonded hydrogen. Sigma bonded hydrogen. So who will stabilize the sigma bond? Sigma bond means hyperconjugation. Means hyperconjugation. And if you will see the order which I discussed with you, what we understand, aromatics are more stable than the miscellaneous. Okay, aromatic and miscellaneous, then comes your lone pair, pi bond and sigma bond. Lone pair means substituted, pi bond means resonance, sigma bond means hyperconjugation. Yes, and then after comes your percentage of S character. Again and again I am repeating so that you will be able to learn the order. Okay, after percentage of S character, anti-aromatic. So these are the 7 things, 4 plus 3, 7, that we have to focus. So ultimately, out of hyperconjugation and out of resonance, which is a more predominating factor, which could be a better nucleophile? Resonance, absolutely, the pi bond. So this is going to be more stable. Example number 7, if you will compare between the two, what is the difference? This carbocation is basically a carbocation which is a part of a ring, but this carbocation is not a part of a ring. So this is, we can say that this is an aromatic carbocation. This comes in the category aromatic carbocation, and we can also say that this is quasi-aromatic, because what are quasi-aromatic? Quasi-aromatic compounds are aromatic in nature, they are also ionic in nature, and here the ion is a part of the ring. Okay, this is quasi-aromatic carbocation. Is this a aromatic carbocation? No, this is aromatic carbocation, and this will be getting stabilized by the resonance. So this is a difference between the resonance stabilized carbocation. This is a resonance stabilized carbocation, and this is an aromatic carbocation. So this is the difference. Otherwise, of course, in the aromaticity, resonance is actually there, है ना? Without delocalization, aromaticity could not be there. But the difference between the aromatic carbocation and the resonance stabilized carbocation. Okay, so who will be more stable? Just now we have seen the order. Aromatics are more stable than the resonance stabilized. So ultimately, this is going to be more stable. Please watch my lecture on quasi-aromatic. Here the example number 8. If you will see both the examples, this is a phenyl carbocation. Phenyl, yeah, the name we give is the phenyl carbocation, and this is basically the acetylene carbocation. But if you will see and compare, you know what? This is a carbocation. Acha, is this having a trigonal planar geometry? No. So as per me, it's not a good carbocation. Okay, because this must have a trigonal planar geometry. As I told you, this is sp2 hybridized. So what we do understand is, we can see that here this carbocation is basically having sp2 hybridization, but here this carbocation is having sp hybridization. So sp2 and sp, here as per this the percentage of s character, if I see, here we do have 33.33 percentage s character, and here we do have 50% s character. Okay, and as the s character increases, the energy decreases. Okay, I told you the energy of p orbital is higher then the s orbital, so if the s character, percentage of s character is increasing, means what? Means the nucleophilicity, if the percentage of s character increases, means the nucleophilicity decreases. The energy, the highest occupied molecular orbital, HOMO, decreases. The energy of the highest occupied molecular orbital decreases. So if it is decreases, the nucleophilicity decreases. This will not be able to stabilize the carbocation better. Okay, so the stability decreases. Ultimately, we can say that the phenylic carbocation is a stable carbocation than this carbocation. Okay, because of the percentage of s character. Got it? Now here, if you will see the example number 9 and you will compare between the two, which is this? There is a ring, and here in the ring, the overlap is not over the sigma bond. There is no headed overlap, but the overlap is slightly bent in nature. This kind of overlap, and because of this kind of overlap, and here we do have a vacant p orbital. They undergo delocalization. This ring will get broken because of this angle, the angle strain. This ring will be broken and will give the electron pair to this. Ultimately, we can get this as a pi bond, this as a carbocation, and so other resonating structures. And because of this reason, this is said to be the miscellaneous carbocation. In which category I put it? Miscellaneous carbocation. And I told you this cyclopropyl carbocation, people say this as a dancing resonance, but please guys, avoid saying dancing resonance. Okay, I want to clear this confusion that you do have. Basically, the concept is of the nucleophilicity. Whosoever will give the electron pair easily will stabilize the carbocation in a better way. The concept is this much only. Okay, so yeah, we can consider this as a miscellaneous carbocation, and this is what type of carbocation? Here at the alpha position we do have a pi bond. So pi bond means there we can have a resonance. Okay, now see the table, see the order which I told you. Aromatic, then comes your miscellaneous, right? After miscellaneous comes your lone pair, pi bond or sigma bond, that is substituted resonance, or hyperconjugation. So relatively miscellaneous is more stable than the resonance. So ultimately we can say that miscellaneous cyclopropyl carbocation, methyl carbocation is more stable than the benzylic carbocation. Now, it's not a ring of your school, it's not a ring of Megha ma'am's lecture. Now, let's have a focus over the example number 10. And in example 10 is the last example. Who would tell me? This is a carbocation. This is the alpha position. Carbocation, alpha position. Here we have nitrogen. Here we have oxygen. This is also having the lone pair. This is also having the lone pair. Now, who will be a better carbocation? Who will stabilize its more better way? Who will be a better nucleophile? Look for which is a better nucleophile. Bacha, don't look over the number of lone pairs, okay? This is the very bad thing a student could do. Don't look over the number of lone pairs. Yeah, over the nitrogen we have 5 valence shell, so we can have only one lone pair, and over the oxygen we have 6 valence shell electrons, 1, 2, 3, 4, 5, 6. So we could have 2 lone pairs, but number of lone pairs doesn't make them more nucleophilic. Basically, guys, we must know a carbon, nitrogen, oxygen, and fluorine. Nitrogen is a better nucleophile than the oxygen than the fluorine. Why? What's the reason? Because as we go from left to right in the period number 2, as we go from left to right, the electronegativity is the factor. As the electronegativity increases, the electron cloud gets more tightly held by the nucleus. Electron gets more tightly held by the nucleus. Since the electrons will be more tightly held by the nucleus, their polarizability decreases. Polarizability means electron giving tendency. Polarizability, that is electron donating tendency, decreases. Donating tendency decreases. Okay, so since the electronegativity increases, the electron giving tendency decreases, so they will not be a better nucleophile. So that's how we can say that nitrogen is a better nucleophile than oxygen. Okay, so that's the reason that nitrogen is a better nucleophile. So nitrogen will stabilize. This is also a substituted case, substituted carbocation, and this is also a substituted carbocation. So if we have to compare between the substituted and substituted carbocation, we can say that this is oxygen and this is nitrogen. So nitrogen is a better donor. Okay, there will be better back bonding by the nitrogen. So this will be a better this will get better stable as compared to that of the methoxy group. Okay, so this is it. This is all what we could learn, we could understand, and this is all about the carbocations and their stability. I hope I have answered all the questions that are in your mind, but still, if you have any single doubt, please do let me know. You are free to ask me anything, whether it's a silly doubt or it's a genuine doubt, it's fine. I'm there to answer you. Okay, so please, guys, I enjoyed giving this lecture to you. If you really enjoyed watching it and have learned something through this, then please hit like and subscribe to our channel, and do share this session with others as well, so that just by bit of bit I could be able to help a large number of people. Okay, so this is the aim of Unacademy, and this is the aim of me as an educator, to help those who can't afford the education at a the quality education. Okay, so that's why we are bringing such quality sessions for you over our YouTube channels. So this is it. Please do follow me on Unacademy if you can really afford, and if you are interested to learn more from us through Unacademy, then guys, we are having a lot of plus courses. Okay, we as a team, we as the top educators over the Unacademy are coming up with very effective lectures for you for your IIT JEE preparation, not only for IIT JEE, many other competitive exams, but yeah, I do take your IIT JEE, so you do join us. I'm also a CSI UGC net qualified with All India rank 25. So basically, this is my All India rank in chemistry. I want that you master this particular subject. I would be able to build interest in you so that you could score maximum out of this particular subject, okay, which is actually very easy to score, because chemistry is actually scoring, and just by putting a bit of efforts you can score a good number, okay, and can qualify the JEE mains examination. So this is what I'm contributing. You do also contribute by hitting like and subscribing for the channel, and do share our videos. Thank you so much, guys. Don't forget to follow us. Bye bye, take care, and do let us know what next you want, okay, and how we could help you in different directions, okay. Take care, have a great day.